Welcome. In this video we're going to learn something about a coin. And with the coin flip as the mother of all experiments, we will ask and answer the question how we can infer information from data, specifically how to do parameter inference. And with this simple experiment, we will try to get a feeling for very commonly applied techniques in statistics and machine learning, such as maximum likelihood, maximum a posteriori, and fully Bayesian analysis. So now assume that we're doing this experiment here. We're using the same coin for 10 flips, and the results is a heads, followed by a tails, followed by 2 heads, followed by a tails, followed by 3 heads, followed by another tails, and lastly another heads. A reasonable question you might ask now is, what is the probability of the next flip, the 11th flip, showing up tails? For example, you might want to place a bet, and it's good to know whether this coin is biased or not, for example. The thing is, these flips are independent of each other. They are conducted with the same coin, but they shouldn't affect each other. And the question is, how can we extrapolate from the 10 observed flips to the 11th not yet observed flip? How do we do that? Well, one thing we know is that the probability for the next flip showing up tails is a number between 0 and 1, because we're dealing with a probability. That's a no-brainer. But the question is, what is a reasonable choice between 0 and 1? And down here you see some of the choices that you have, but you could, in principle, choose any number. Now, if I give you a couple of seconds to think about what number you would suggest, then my guess is most of you would come up with one of two choices. One part of you would come up with 0.5. And the rationale behind this is that we have no information about the coin, so we should assume it's fair. And that's a reasonable choice. The second group, I would guess, would come up with 0.3 as the answer. And those who do that probably looked at the sequence and observed that we had 3 tails in our sequence of 10 flips, and 3 over 10 turns out to be 0.3. And we could say, okay, if we observe it 3 out of 10 times, then we can assume that it's going to continue like that. Now, the question is, can we, in some more rigorous sense, give an argument as to why one of these choices or any other choice is reasonable? And this is the question that this lecture or this video is going to answer. So by looking at the data at hand, the flips we observed, we found that 30% might be a reasonable choice as the probability for the next flip being tails. It seemed reasonable, but we cannot really argue why yet. And in order to do this, we need to formalize our coin flip. We need to find a formal language for the random experiment in order to be able to draw conclusions about it. Now, every flip is random, so the framework that we use is obviously probability theory. And what we do is we have a parameter, an unknown parameter, theta I, for the ith flip, that tells us whether the flip I, denoted by this random variable fi, will show up tails. And what we want to do is we want to find out more about this parameter theta I, or this set of parameters theta I, from the data. So we have probability distributions pi, one for each coin flip, and it depends on this parameter theta I. And in order to highlight this, there's another notation we're going to use very often, not just in this video, but also in the upcoming videos, which is that we put this parameter, this unknown parameter, in there as a condition, in order to say, okay, this probability of the flip I showing up tails depends on this parameter theta I. Okay, and what we're trying to do when answering this question, what is the probability that the 11th flip shows up tails, is we're actually trying to reason about the parameter theta 11, because it's the 11th flip. And theta 11 tells us what is the probability of the 11th flip being tails. Now the thing is, the data that we have only comes from experiments that depend on the parameters theta 1 through theta 10. And that's a problem because how can we extrapolate to theta 11? So theta 11 is still problematic. For the moment, we'll thus stick to what we have, which is theta 1 through theta 10, and the observed sequence. And this observed sequence has a probability of being observed, which depends on parameters theta 1 through theta 10. That's what's written down here. Okay, so what do we know about these parameters theta 1 through theta 10? And are they in some way connected through theta 11? The connection is not obvious, but we can now start to do something which is called maximum likelihood estimation. Maximum likelihood estimation is a very common principle. A lot of machine learning algorithms actually boil down to a maximum likelihood estimation at the core. And that's why it's very important that we take a close look at it. What maximum likelihood estimation does is the following. It looks at a probability of data, a so-called likelihood. That's this term here, or also this term is the same. And it tries to find those parameters theta 1 through theta 10 that maximize the value of this likelihood or probability of this sequence. So we want to choose those parameters under which our observations become the most likely. And that's why it's called the maximum likelihood estimation. And that seems like a pretty reasonable choice. And it's also a very formalized choice. So maybe this will be the path to justifying one of the values we discussed previously. So let's set out to maximize the likelihood. It turns out that there's one big obstacle still in our way. And that is that we don't really know how this likelihood actually looks like. And the reason for this is that we haven't specified the full model actually. And in order to do this, we need to introduce further assumptions. And the first assumption is independence. Independence means that we are assuming that the observations that we made, in our case the coin flips, they are from the same source, but they are not affected. They're not affecting each other. So this means the first flip, the outcome of the first flip, does not affect the outcome of the second flip. And mathematically, this implies that the complicated likelihood term that we're struggling with simplifies into a product of 10 simpler factors. And then we can also introduce this shorthand notation, which is just this normal product of these 10 factors. Now, this is already much nicer because we already talked about these simple factors, but the problem is they are all depending on the I, on the theta I in particular. And that means there is still no theta 11 in the equation. And that's reasonable. I mean, these coin flips, they can happen at different times, on different days, for example. So it could be that the theta I is different. But actually, typically these happen under similar circumstances, and the coin and the experimental setup does not change significantly. And this is another assumption we will need to introduce. So we found that independence simplifies our likelihood model, but the problem is we still had no connection to theta 11. And we also had no connection between the theta 1 through theta 10. But we also said that these coin flips, they are happening under similar circumstances. So that makes the second assumption reasonable, which is called identical distribution. Identical distribution means that we're dropping the I of the parameter. So that means that we're assuming that all 10 coin flips that we observed are governed by the same parameter theta. So instead of 10 different parameters for 10 coin flips, we have one parameter that governs all the coin flips. And this is also the point where we're connecting the first 10 coin flips to the 11th coin flip. We're saying that this one parameter theta is governing the first 10 flips that we already observed, and also the 11th coin flip that we haven't observed yet. And this is going to be the key for inference. And because these two assumptions that we introduced right now are often used together and are used in a lot of different places, often even implicitly without stating it, they have a special name. So we have independence and identical distribution, and often what you only see is this shorthand notation, this abbreviation IID. If you hear someone say, my data is IID, what they mean is, I'm assuming this data was gathered from a process that is independent and that is identical in distribution. Okay? And as I said, this is the link between the first 10 flips and the 11th flip, and in particular the parameters. And now we can actually explicitly write down the likelihood that we're trying to optimize. Remember that theta was defined as the probability of the flip showing up tails. So because we had this sequence of head, tails, 2 heads, tails, 3 heads, tails, and another heads, that was the sequence that we observed, we get this likelihood. So 1 minus theta is the likelihood of heads, and theta is the likelihood of tails. And now we can just use basic algebra, and our likelihood simplifies to this very simple, very short term theta to the power of 3, which is the number of tails that we observed, times 1 minus theta to the power of 7. So by these very broad and very intuitive assumptions, IID, we simplified our likelihood to the point where we can start optimizing for the parameter theta. So let's summarize. We've introduced two model assumptions, independence and identical distribution. And it turns out that this simplifies our likelihood assumption greatly to a fairly simple polynomial. And now remember that we set out to maximize the likelihood. So what we do now is we interpret this polynomial simply as a function f of theta. That's our likelihood. And we want to maximize it. And you know how to do this from high school analysis. So what we need to do is we need to take the derivative with respect to theta of this function f and then find the critical points by setting it to 0 and solving for theta. And you may remember the critical points are either the maxima or the minima, or there's another case, a third case, the saddle points. So whenever the slope of the function becomes 0. And we would like to avoid the second and the third case. And to check that, you insert the critical point into the second derivative and check for the curvature, and then you get your maximas. Okay, so in principle this is easy, in particular when you deal with polynomials, but taking the second derivative here already becomes pretty ugly because you need to use the product rule and you get a lot of terms. So it's doable, but it's very technical and it requires a lot of work. And to ease some of the pain of these calculations, we're going to apply a trick. And this trick is that monotonic functions preserve the critical points. Okay, so let's digest this. First of all, what does monotonic function mean? It means one of two cases. So in the first case, if x1 is smaller than x2, we pick 2 points on the x-axis. This implies that the functional value also increases. So the smaller, the bigger the x value, the bigger also the function value. Okay? And this is a monotonically increasing function. And if there's a monotonically increasing function, then there's also a monotonically decreasing function. So if I have the same setup of x, this implies that the functional value is always decreasing, okay? And one example of a monotonic function, in fact a monotonically increasing function, is the logarithm. So recall what the logarithm looks like. It's defined for positive x's, and it looks a bit like this, okay? So for 0, it tends to minus infinity, and at 1, it's 0, and it's monotonically increasing, and it grows beyond any boundary, okay? So now don't get confused by this. What this box is implying is not that the value of the maximum is the same, okay? Obviously, because we're applying the log, the value of the maximum changes. But we're not really interested in the value of the maximum, but in the position of the maximum. And what this hint or this trick tells us is that when we apply a monotonic function, the position of the critical points, and in particular the position of the maximum, does not change. And this will turn out to be a very handy trick. So we wanted to maximize the likelihood. And this means we want to maximize this term theta to the third times 1 minus theta to the 7 with respect to theta. And moreover, we're actually interested in the position of the maximum rather than the maximum. So what we're doing is an argmax. Argmax means we want to know the value of theta where this function is maximized rather than the maximal function value. And now this monotonic function trick implies that this is actually the same as finding the argmax with respect to theta of the log of theta to the third times 1 minus theta to the 7. And now we're going to see why this is actually such a nice trick. Well, we just apply the logarithm rules, and we find that this is actually the same as 3 times the logarithm of theta plus 7 times the logarithm of 1 minus theta. Okay, and this is a much simpler function. It doesn't look simpler, but taking the derivatives of this function is much simpler than the polynomial we had previously. Okay, and now we can again take first and second derivative and look for the critical points. Okay. And I define this as the function g of theta, and this is called the log likelihood. And now the derivative d with respect to d theta of g of theta is actually, let's do it in the most general form, that is the number of tails times 1 over theta. 1 over theta is the derivative of the log of theta plus the number of heads times 1 over 1 minus theta times minus 1. Okay, don't forget this minus 1. The minus 1 comes from the chain rule because we're taking the derivative with respect to 1 minus theta. The derivative of 1 minus theta with respect to theta is minus 1. Okay, don't forget that because it will screw up all your calculations if you miss that. And now this is supposed to be 0 if we are looking for critical points. And if you do some calculations, try to do them yourself. What you will see is that this is the case if theta is the number of tails over the number of tails plus the number of heads, and that is to say the number of total flips. Okay? And now what we would need to do is we would need to insert this into the second derivative and verify that it's actually a maximum, but I'll skip this step at this point. You can just believe me, this is actually a maximum. And this maximum is what we call the maximum likelihood estimate for theta. Okay? This particular theta is the one that makes our observed sequence the most likely. Okay? And if you observe this closely, and if you insert the values 3 and 7 from our particular sequence, what you see is that it's 0.3 in our case. Okay? And this is the justification for why 0.3 was a reasonable choice on the second slide. Okay? And this 30% now is justified by the fact that we expect the coin flips to continue as they started. And the sequence that we observed so far is most probable for theta equal to 0.3. And the nice thing is this works for any sequence. So whenever you do another 200 coin flips, you can update your maximum likelihood estimate. Okay? So we have found that the maximum likelihood estimate explains our intuition when we look at data, and that's very nice.